Okay, so continuing our journey of knowledge, we have Professor Chetan Singh Thakur, who would be sharing his insights on neuromorphic computing. A small glimpse about Professor Chetan: he is a faculty at the Indian Institute of Science, Bangalore. He has received his PhD in neuromorphic engineering at the Marx Research Institute, Western Sydney University, and did his postdoc at the Johns Hopkins University, USA. He also worked for a few years with Texas Instruments Singapore as a senior integrated circuit design engineer. His research interest is to understand the computing principles of the brain and apply it to build novel intelligent VLSI systems. He has received several awards such as INAE Young Investigator Award, Pratiksha Trust Young Investigator Award, and Inspire Faculty Award from DST for brain-inspired computing. So ladies and gentlemen, let's give a warm welcome to Professor Chetan Singh Thakur.
All right, thank you so much, Marvin family, to invite me here. And thank you, Mr. Hemchandra, for personally inviting me at ISC. Today, by the way, it's good to see some real hardware training in India, right? Because generally when we talk about, we have a lot of engineers, but mainly they are being, somehow they're obsessed with IT and computer science, and then they really miss this, the real engineering, right? And good to see the courses which are really focusing on the hardware side of it, like VLSI, and good to see this new course which is embedded. And I was mentioning that nowadays, all this modern electronic system is nothing but embedded. You can't just say, okay, I'm only embedded software, I'm only embedded hardwares, and so on, right? As an engineer, you should know from end to end, then only you can optimize, because you can't just work in silos and so on, right? So good to see that course, and I've seen this curriculum, it looks really nice. They have some hardware components, microarchitectures, microprocessors, and also some ML flavor into that, so that you can go into the direction of tiny ML or edge computing. So good to see that. Anyway, so today's talk, I'll focusing on, give you the brief overview on this neuromorphic computing, the quest to mimic the brain. How many people are aware of this term neuromorphic computing? Just please raise your hand just to get an idea. Oh, looks like no one, or maybe few. All right. By name itself, or I would just simplify this neuromorphic term, is nothing but brain-inspired computing, right? And if you see as an engineer, right, we always focus on this power, performance, and area matrix. Is that right? Whenever you go to any company, they say, okay, these are the three metrics: power, performance, and area. Now take a look at the brain, right? We have very small, this 3D system, and we have almost like 100 billion neurons, right? Each neurons are doing some computations. You have 100 trillion synapses, which is more like a memory, right? It's a huge memory there, and it's not a binary memory. It's a multi-state memories. You can think that way as an engineer, right? And as an area and weights, right, which is only 1.5 kg, right? It's a massive system which is being evolved during evolution process, right? Billions years of evolution process. And nowhere we are close to it, and probably I would say even next 100 years would be dedicated to this. So we are not close. So don't worry about it, even if people talk about AI and so on. Okay, they are very focused, but we are more like a general intelligence. All right. Okay, so as I said, right, we are nowhere close. We don't understand how it works. First of all, if you ask any neuroscientist, they'll say, okay, I know probably 1% or 2% of the brain, but because the technology now, they're trying to poke a little more, trying to get more data from a small area. Maximum, when you saw this link from Elon Musk and so on, right? There are 1,000 electrodes, right? So, but I'm talking about 100 billion neurons. And it's a big dynamical systems, okay? It's not like you just, like in typical AI, you see feed forward, right? You have this inputs coming in, then you have multi-layers, and you see output. It's a big, giant dynamical system, and you know as an engineer, if in any control system, if you put 2 state variables or 3 state variables, you don't know how the system is behaving. It becomes chaos and so on, right? And here we are talking 100 billion different state variables working together and so on, right? So it's a massive system, difficult to understand. People are trying to understand, and that's the goal of this neuromorphic community. Can we understand those principles, right? Some of those principles, and try to build intelligent systems. That's the goal here, right? And that's what we are working on. By training, I'm an engineer, but we try to get this inspiration from the human brain or any general nervous systems, right? Because that's the gold standard, we can say, where we have to achieve. And that's a good thing about this technology, where you know where to reach for, right? Unlike any other technology in quantum, right? For example, when you talk about quantum computing, you don't know what would be the gold standard or where you will be reaching. But here, at least you know this is my gold standard, and you know the path forward, where to reach for, right? So that's the good thing about it. At least some optimistic you can think about. Anyway, and please feel free to stop me. I was mentioning Hemchandra as well because I will take my professor hat and start just talking about whole day. So please stop me whenever you feel. Okay, before I delve into the detail, this is broadly, our lab at ISC Bangalore works in this area, which is more in different segments of different verticals of neuromorphic. One is neuromorphic VLSI. For example, we try to understand different pathways, acoustic pathways from cochlea to the acoustic auditory cortex, and maybe vision from retina to V1, V2, and IT area. And then these are the two sensors, which is little different from your conventional sensor, right? So this is silicon retina, which is try to model the retina, and you build those retinal image sensors. So in conventional your phone, right? These are very dumb image sensor. It doesn't do anything. It just take the, there are a bunch of photodiodes, right? Which is when you talk about the pixel, 1 megapixel. This is a 1 million photodiode. Light falls into it, it converts into current, and that current will convert into voltage, and then you put the ADC and you sample it. And you reconstruct, very dumb. On the other hand, our retina does lot of computations. You get giga samples of data per second, and after the retina, you get only 1 MB per second. So a lot of compression, a lot of computation is going on there, right? So on that model, this silicon retina has been built. Similarly, we work on the cochlea, which is acoustic, where we always underestimate because we are visual animals, right? We have almost 40% area of the brain is dedicated to vision, right? And we generally don't bother about acoustic. If I ask, how many people have heard the cochlea? Right, very few, right? But if I ask how many people knows eye, almost everyone knows, right? So that's the difference. So, but in evolutionary, during the evolution process, acoustic came first because for the survival you need acoustic. It's not in the field of view you have to be, right. In those days it was forest and so on, and you have to survive, right. So those sensory modality has evolved first. So it's for the survival. This vision came much later actually. Anyway, so these are the two sensing modality which we work on, and the third part is more on the AI architecture. Everyone is talking about these days AI, and you should be aware of that. So this is mainly for edge computing and TinyML context. So we built our own AI co-processor. We built analog based circuits or digital based circuit. I'll talk about that as well. And then other thing is more like a neural simulator. We try to model with analog circuits different neurons and synapses model, right? I was talking about in the brain, you have these basic elements, neurons and synapses, right? These are the computational elements. So can you model those principles with silicon area or with silicon substrate and see what happens? And those kind of spiking neural networks built with analog circuits, we try to use for BCI application, which is in the bottom you can see here. So at ISC we have these primate research facilities where we have these monkeys and so on, and neuroscience. We have a very strong center for neuroscience where people do this kind of experiment. So we are trying to develop this brain-computer interface, those kind of things, which I have just said the anecdote what Elon Musk is doing, but we are much smaller scales and try to understand more on the science part of it. So this is broadly in the neuromorphic area we work, but also we have some other area like medical devices and quantum computing. We built 4-qubit quantum processor in India, and that's what we have in ISC along with my colleagues from physics department. So this is broadly what we do. Now let's go back to what is neuromorphic engineering, right? So this field, as I said, right, the idea was it started in late 80s from Caltech, and the idea was, can you build the electronic system inspired by function, structure, and physical foundation of how the brain works, right? Or underlying principle, how this underlying signal processing principles is there inside the brain, and can you learn those principles and can you build on silicon? That's the idea. And yeah, these are some of the numbers. Brain is 10 million times more efficient than the best digital technology. And as I said, right, roughly how much power we take? Human brain, how much power it takes? Anyone? Any wild guess? Anyone? In watts, kilowatts, megawatts, milliwatts? No idea? Huh? Milliwatts? No. Yeah, so it's around 20 watts, which is just one bulb. Now I'll show you some number when we talk about this ChatGPT 3 and so on, right? It generally requires megawatts of power just for the inference. Forget about the training and other part. So you are burning megawatts of power just to train for NLP, natural language processing. But we are doing everything in 20 watts of power, right? So fundamentally, there is a difference in terms of architecture and the way we work, right? Okay, so it's highly engineered system. And even if you learn even a small thing, that would be great for as an engineer. Okay, so I'll skip this part. So this is one of the most emerging technology, and it has been part of this 10 breakthrough technology from MIT. And there was a lot of things going on in this around the world. There was a human brain projects of around 1 billion euro cost, and one of the vertical was neuromorphic computing platform. There was a brain initiative from US that's around 1 billion USD by Obama. He has announced. So a lot of work is going on around the world. In fact, there is a lot of companies involved, big players like IBM and Intel, and they have built their own this neuromorphic processors and so on, right? So it's one of the emerging technology. And at ISC also, we have one of the strong group where we have people from neuroscience, we have people from signal processing, and people like me who is more into the VLSI and integrated circuits. So we work on together and building some kind of this kind of systems. Okay, so before we delve into detail, I would like to motivate the audience why it is so interesting, right? And I found that people have no idea the kind of optimization we have already happening inside the human brain, right? So biology is a highly efficient machine, right? And I'll give you this one example here. This bee, right? Which is, the body weight is less than 1 gram, right? And brain weight is only few microgram. And it has almost 1 million neurons into that. And you can see that a small bee can roam around into this, in the field, find food, find a mate, and so on, right? Only in 1 million or in few microgram and few 10 microwatts of power. Now tell me any system or any robots people have built up this capability. Nowhere close to it, right? So biology has evolved with such a great details, and also, as I said, the architecture is fundamentally different. The kind of architecture we talk about is von Neumann architecture. Everything is digital, 1 and 0 and so on, right? But that's now how the brain is. If you go inside and if you find those details, you'll find it's more like a mixed signal design, I would say. As an engineer, I would just want to give the analogy. It's more like a mixed signal design, where the computation is happening in analog domain, where you want to use the full potential of your transistor, right? But if you just use transistor as a 1 and 0, then just a binary, you are just using as a switch. But if you see a single transistor is highly powerful. With single transistor, if you know, the current and voltage relationship is square law. In strong inversion, if you go to sub-threshold, it's an exponential law, and so on. So you can do exponential function, a square function with just one transistor. But now, when you go to digital, you suddenly make it as a switch, and you just lose all the property. All the physics behind is gone, right? And that makes a huge difference. Another interesting fact I would talk about, because I think you all have this background, so I can take this another example. If I ask you to build a 2 8-bit multiplication or 8-bit multiplier, it would take roughly 40 to 50,000 gates. Is that right? Roughly, right? Now, if you want to build 2-bit multiplications, you can do with 3 or 4 transistors, right? Like you might have heard Gilbert multipliers, or if you use current and voltage as a variable, and then you can just flow it through, and you can use this KCLs and other device physics, and you can build a multiplier with few transistors, right? So you can see the order of magnitude difference in terms of powers and area, right? And that's what we are missing. But biology has taken care of this nicely, and we have to understand that. Okay, so the idea is, can we learn from nature? These are some of the brain facts which I want to put it here so that you are aware what the kind of technology you are roaming around with. Okay, and again, all you are engineers, so I want to just give you those numbers. So the brain power is almost, roughly 20 watts or 18 watts of power, which is just a one bulb, right? And you can calculate this by how much food you take, right? You roughly, as an adult, you take 2,400 calories, and people have measured the volume, how much volume flows through this main artery which goes to the brain, and then you can calculate that number. So that number is calculated that way, right? How much, and roughly it comes around 20 watts of power. Weight is 1.5 kg, this whole mass, which is almost like a only 2% of the body weight. If you see roughly, it's 2% of the body weight. But in terms of body, it's highly power hungry. It takes 20% of the whole body. Whatever you are eating, most of the power goes here. Okay, but still it is much, much low power. Neuron is around 100 billion neurons, so you can imagine you have 100 billions basic element which is doing computations. 100 trillion synapses, so almost one neuron is connected to roughly 10,000 neurons. So you can see again, as an engineer, you can think about the fan-out issues, which is the major issues in your circuit, right? Routing is the biggest issue, right? Not the element. How do you route it? How do you do these connections, right? But brain has evolved to do that. So there is various different connectivity. They have locally connections, dense connection, but far away you have sparse connectivity. Okay, so can you use some of those principles when you build this scalable system? So those are the ideas. And yeah, and you're losing neuron every second, by the way. Right? Imagine now if your chip is losing every transistor, even one day even one transistor can make an havoc in your chip, right? But we are losing every second. And of course, you have 100 billion, so even if you lose every second, in 80 years, still you have enough neurons to work with. And that's why when you go age, then you have this dementia and other problems comes in, right? But this is happening. But still it's much, much robust. You are not forgetting your wife or husband, right? Even every other day, you still remember that, yeah. Unless you want to. This is a separate issue. Okay. Okay, so these are, so as an engineer, this is, you see from top down, right? There's the cortical area at the top on the left side. When you come down, there's a pyramidal cell which is in the cortex. When you come down, you see at the neurons and synapses level, and when you come down, that's an ion channel, right? So that's kind of hierarchy you will see into the nervous system. On the other hand, engineers always think about synthesis, right? You start with the basic element. You pick a transistors. From transistor, you make a gate. From gate, you make a combinational logic or sequential logic. From there, you build the circuits and so on, right? So and fundamentally, if you see here, when this field started, Professor Kawamid from Caltech, he found a nice analogy. The flow of ions across this channel follows the Boltzmann distribution. Okay? Same thing happening when you use your transistor in subthreshold region, when you have this diffusion process that follows the Boltzmann distribution. So by controlling the gate, right, you change the barrier. And that's the physical law. So that's happening in transistor. That same physical law is happening in ion channel. And from that, they try to start mimicking that. So at fundamental physics level, both are same. Both follow the same physical law. And that's the main idea about starting this field. And then people trying to build up this from ground up. Okay, so quick comparison between brain and computer, right? If you see, basic unit is neuron. On the other hand, if you see computers, right? I'm talking about the standard computer which is everywhere these days in your laptops and mobiles and or whatever the system you talk about, mainly this digital part, right? They're used as a switch, right? As I was pointing out, right? And as an engineer, you just don't care what is going on beneath, right? You just use as a binary switch, 1 and 0, right? When you talk about binary, you have no idea how the transition is happening. People don't care, right? And brain is imprecise. If you poke any neuron, which is common experiment neuroscience people do, that they take out a neuron, they do voltage clamp, and then they apply current. They literally apply current, and you see the firing rate. So neuron responds to that. So if you apply 1 microampere current to this neuron, real neuron, you will see some firing pattern, something like that. Next time again you apply, but it's some kind of distribution. The distribution would be the same, but let's see, initially at first time it would be 100 hertz, second time might be 90 hertz, third time it would be 110 hertz. So it's a distribution, it's not accurate, it's not precise. That's what I'm trying to say, it's not repeatable. But in transistor, if you apply a voltage, you will get 1, if you remove, it's 0. Very precise, determinate, that's what the whole industry is working, right? That's why you're trying to find a bug. It should work in all the conditions, it should give 1 always. But also make it very prone to noise, because if it's stuck to 0, when people in DFT do, it's stuck to 1, stuck to 0, all this testing, right? Fault testing. But if it is stuck to 1, the whole chip is gone. So there is no robustness, there is no noise tolerant is there. right? On the other hand, brain, if you see, the average firing rate is close to 10 sometime or 100 hertz. Let's see, 100 hertz you're talking about. Now the PC or computer you're talking about 1 gig, 2 gig, right? And there's no fundamental clock as such. We are completely, there's no global clock running here, right? It's a completely asynchronous system. That's what I said, it's a big dynamical system, okay? And that's what when you get this epileptic seizure, then this system becomes unstable. You have a positive feedback, that's why you suddenly get all this start firing, right? And that's what this epileptic seizure comes in. That's one of the model people have proposed from the knowledge of control systems. Component failure, as I said, we are losing neuron every other second, but still we are fine. And this fundamentally is on learning paradigm, right? And the existing computer system is more on the software paradigm, right? You already aware of your underlying algorithms, and then you code it up, right? You already know, let's say you want to implement FFT, right? You already know FFT and you code it up. Here, if I ask a kid to ride a bicycle, he doesn't know how to do that, right? It try once, fall, try another time, fall. It doesn't know this underlying function, what he has to optimize, what he has to learn, right? So it's learn, there's no programming. So underlying principle is very, very different, right? And these are some of the other number which I will skip, which we already talked about. Right, so ideas, can we learn those? Okay, now today I'll talk about this three system, this two sensory modality, which is one is the cochlea, which is, I want to give you some idea and how people have modeled the cochlea into silicon and how it has been very useful to do that. And second is the silicon retina, and if time permits, I'll go to some of the circuit which we built. Okay, fact about cochlea, and I already know a lot of people don't know. So this is, so you have seen this ear, right? This is outer ear, correct? Which is this pinna. By the way, why do we need pinna? Anyway, I'll come to that later. But this is outer ear, right? And the sound goes in, and it's such a fantastic system. You get the sound energy, right? And then that sound energy get converted by these three bones, tiniest bone in your body, into mechanical energy, right? Sound comes in, then it converts into vibrations, right? So you need a right impedance matching, right? You might have heard this transfer, this 50-50% transfer. You need to have 50-50 impedance for transferring the energy, right? Or power, right? 50% power transfer function, this rule. And then from mechanical, then cochlea converts that mechanical energy into electrical energy, which is nothing but a voltage spike, which is the neuronal spike, right? The language of the brain is spike, which is voltage, right? 1, 0, and that's actual voltage, 100 millivolt. The range is 100 millivolt. If you open it up, it is 100 millivolt. So they have a battery, which comes from the ion channel. So it's proper electrical signaling there. Okay, now if you go inside, there's a nice snail shape structure there, which is in a simplistic way you can think about as a mechanical fast Fourier transform, which converts your sound, which is coming from external world, into different frequency bands. Okay, of course it's more than that. So it has this 3500 inner hair cells. So it has three main components. One is the basilar membrane, which is, you can think about the sheet of Fourier transform, right? And then on top of that you have inner hair cell, which is nothing but some kind of neuron. And based on the sound signal, different parts, because as I said, let's say you put a single tone, this part is vibrate, right? Because of the thickness, you have different resonant frequency of that membrane, right? And based on that vibration, you pick up this vibration, and that's basically has a tonotopic mapping in the auditory cortex. And that's what you understand or you perceive the sound. So when I'm saying this all happening in your ear, and then you have this 12,000 outer hair cell, which controls. If you see that you are so good in this high dynamic range, you are able to hear very tiny whisper when somebody is talking, and you are also able to hear very loud sound which is coming from the jet. And if you see the dynamic range is like 120 dB, and there's no microphone which can support that. So it's a huge 120 dynamic range, which is like 10 to the power 6, 1 million, order of million, right? That kind of difference in audio signal you are able to hear, and because of this outer hair cells. Any question, or you are getting bored? Okay. Yeah. So I'll just play this thing quickly, just to showing the functionality. This is just a nice simple animation which explains you how it works. That's the cochlea. So it is just for the explanation, it is unrolling, but it's like a snail shape, actually of this shape. So if it is single tone, only one part will vibrate. This complex tone which has multiple frequency band, right? So this is what is happening inside if you hear. And on top of that, imagine there is a cell residing on top of it, and when it vibrates, that vibration is picked up by those cells. I'll play this another sound, which is outer hair cells, which controls the dynamic range, which is 120 dB dynamic range. And you'll see this is actual cell from the pig. They have removed the pig. It's still outer hair cells control the gain of your filters actually, which is, and that's what happening in real time. And because of this, you get this hearing problem in old age. So that's the culprit. Okay, and this is, then we model everything, this outer hair cells, inner hair cells, and basal membrane into the silicon chip. We build the silicon chip. Now we use it for front-end application. So whatever you do, any work with relative sound, this is the actual model we use, and we see all this behavior, whatever I've shown you. So that's the background. These are, I'll skip this part. Again, the same model we also implement on FPGA so that you can build some AI processor along with this for acoustic applications. And this is the output of that, from that. Okay, so I'll skip this part, all this. And then I was talking about this localization, right? That's very, very important. So and that's the reason you have this two ear, right? Otherwise, one ear is fine, right? But how do you localize somebody is calling from here or here? That's why you need this two cochlea. And then you have MSO, which is in medial superior olive, where all this you do this coincident detections neurons, and then based on that, this model is azimuth. So now this is good. But now what will happen if I click here, or if I click here, the distance to reach the sound is same, right? If it is circle, right? It will reach from here at the same time, here at the same. But how do you identify this from here or here? The elevation. And that's what you have this pinna, which has these grooves, which act as a filters. This act as a filter, and this is signature for individual person. So now if I remove this by mistake or by accident, if this is being removed, you'll not be able to hear. But if you put some artificial, over the time, your brain will learn this new features. And that's the reason you have this growth, not for wearing the glass. Okay. And see, this is actually being used in World War I and World War II, because at that time this technology was not available. So they used to use this big ear, so that now the distance between 2 ears is huge, right? So now you will be able to resolve much finer, and that's why they used to stand like this when the plane is coming. They used to say, okay, now attack. So of course this latency is huge, but still that kind of technology is good enough for that. So people used to stand like this in the war and then try to, because radar was not available that time. So this kind of localization people used to do that time. And this is one of the favorite video in the nature you see for survival.
For the tiny sounds of its prey moving about below. but must take great care not to scare them away.
Yeah, so the survival, you need all this, and that's what is beautiful during the evolution process. We have such a nice sensory system, which is even difficult to engineer even now. And now, then, same thing we did. We took 2 cochlea, put onto the system. This was 2 chips, and try to model the same similar stuff and try to do localization. So that was all about this work where we used the silicon cochlea. And then we use this again now, as I said, we work in all this domain for either FPGA, analog. We don't discriminate whether analog and digital. Based on the use case, we choose what system would be best. And we also build this with simple microprocessor or microcontroller, I would say. And then we deploy this in with simple microcontroller, and you can see one of the deployment here. And we deployed in one of the northeast area for ecological application. We created this sensor network where the pre-processing is happening with simple cochlea model, and we deploy like in numbers and try to connect with the LoRaWAN connectivity so that everything is happening locally, and the battery used to support up to 6 months. And you can do this, so this is mainly for poaching related cases we did, so that whenever people are cutting the tree or some gunshot and so on, so that in real time you can communicate to because in the forest you really need low power. You could just deploy and forget for a couple of months. So that was one of the applications we did it. Next, I will just quickly go through the middle part, last part we'll see. So then the retina, right, as I said, right, this is very interesting system. We have, people are talking 1 megapixel, 2 megapixel and so on. We have 135 million megapixel, 135 megapixel I would say, which has this different, almost like a 95 million or 95% of these are grayscale. It doesn't have color. We have only 5% which has color, and that's also in the center, in the fovea. So by default, you're not seeing any color in your wider vision. It's just you fill up with your mind. But there's no photoreceptor in your peripheral. It's only in the center. And also that's what every time when you look, you always saccade, right? You saccade so that you fill up all those gaps. At a time, you have only very small vision. But over the time, you keep saccading and you feel that you are seeing the world in one go, but that's not happening. And it has a lot of computational primitives inside. So the photoreceptor is only this part, right? Only this part is the photoreceptor, which is equivalent to the photodiode in your image sensor, right? As I said, you take this image sensor or this photodiode, you convert into a voltage, right? But here, you can see there are a lot of interesting cells, which is horizontal cells, bipolar cells, ganglion cells. These are actual computational primitive, which is doing computation there. And you get this 36 gigabytes per second HDR raw image, and which is compressed to only 20 megapixel megabytes per second, which is coming off this optic nerve. So a lot of compression, a lot of compression already been done because you can't handle that much amount of data, right? So it's a very interesting sensor. Okay, and the power number is few milliwatts, right? 3 to 4 milliwatts, which is coming up, right? And no image sensor would be able to match that. Okay, so now this based on not all those principles because sometimes you are not able to replicate. So it is, here we are using this some of the cells over there, and it is asynchronous in nature. There is no analog to digital converter. Very high temporal resolution. So what it does, whenever you see the change in the environment, then only that particular photodiode will react. Otherwise, it just keeps silent. Because if there is no information, there is no point of generating the data, right? Imagine if you look at the wall, and if nothing is happening, you're generating gigabytes of data with of no use. But if you put this camera, if there's no new activity, new change, nothing is happening. And I'll quickly, and again, some of this number, which is very high temporal resolution in tens of microseconds, so very high dynamic, like 120 dB. And I'll skip this operation, the pixel, how does it work in the interest of time. I'll show this again videos because people like videos and demos. So this is the principle. Standard camera, if you just keep flushing, you keep collecting the data at the top frame. But the output of this camera would be like this. Only it will show the change, right? And if there's no change in the environment, it doesn't give any output, which is what you want, right? So it's pretty good. It's not for photography, but it's good for a lot of this perceptual or control system application, right? Or maybe for AI ML, where you need low power, mainly for edge computing applications. And we did a lot of work, but maybe some other day. So this is in the lab we are doing, and you can see this is what the output is coming, and this is happening in real time on a small microcontroller. But imagine if you want to do this object tracking with typical camera, you need a lot of resources to do the same thing. And this little more details. Okay. This is another from my colleague. If you see here in okay, maybe I'll skip this. Okay, I'll show you this one pretty old. Now with this single camera, it's playing the Robo Goalie game. It's really fast. As I said, the temporal resolution is really, really high at order of microsecond. And single camera is able to do that in real time with simple micro, because the data is already very, this is what it is seeing. So automatically your segmentation is done. You don't need fancy algorithm here. And really useful for robotic applications. Another example is this pencil balancing, right? Where you put this two cameras on the side. Because the response is so fast, it's able to balance that with this in real time. And very simple algorithm. You see, you just see the tilt in one direction and apply the controls on the other side. And if you do it with normal camera, it's pretty hard task to do this. Okay, how much, do I have any more time? 2-3 minutes, I'll just, or close?
Continue.
Okay. Okay, now the third vertical is this, this part, which is the silicon. So I'm trying to give the analogy, like this is the sensory system, and then this is our computation, right? So on computation side, what are the things which we have built? One of the thing is, and as I said, we have multiple verticals. One of the chipset which we built is completely analog AI chip. If you can look for, you can search for Aryabhat chip, which came out from our lab. This is completely analog processor, which works on microwatts of power, mainly for edge computing applications. And then similarly, we have this Raman processor, which is more like an IP. It's like a microarchitecture. You can run any this CNN types of AI model onto it, any kind of mobile, like mobile nets and DSS CNN and all sort of stuff, milliwatts of power. So it's, as I said, it's like a soft IP. You can deploy in Xilinx board, you can deploy in Altera board, you can deploy in your own board, you can build your own SoC if you want to build it, because it's digital. But analog, you can't do that. So this analog is more like an FPA. We build this field programmable analog array where you can program this analog circuits to do these computations. So that's the idea. The third one is more like a tiny ML on microcontroller, which I've shown you the example for this acoustic, which we deployed in the Northeast area. And these are some of the emerging devices where we use this memristors and sort of stuff. So these are different verticals in the AI and neuromorphic verticals. This is, again, we built this one chip based on this olfactory system, where you have all principle from the olfactory system. I'll not go into the detail, but the whole chip, which is 1 mm square chip, which is in 65 nanometer process, which does this really takes few microwatts of power and does that computation, mainly for perception task. This is that Aryabhat chip, which I was talking about. It's more like a field programmable array. Okay, those who are from analog background, they might appreciate, because this is more like a process scalable. Like in digital, if you write a Verilog code, the same Verilog code you can use in 65 nanometer, 28 nanometer, and 5 nanometer, right? Of course, there will be some pipelining, other things, timing you have to take care. But analog, even if you make one amplifier in 65, you have to come down to 20, and again you have to redo it, right? But the idea is, can you make this process scalable? So we make this field programmable more like a digital, but it's completely analog. So it's a process scalable. We have shown this in 7 nanometer process node as well. And bias is scalable. So the same circuit, because in analog, the problem is use device physics. So in strong inversion, you use the square law. In subthreshold, you use exponential law, and you design circuit based on that. But the underlying system here is a bias scalable. You crank the current, and you can go in any direction, because we use fundamentally different principle here to do that. So that's, and this is Raman AI core processor. All this available in public domain. You can go to the website and you can find all the details about the publication. As I said, this is more like a more like a IP, which you can plug in for various applications. We are using for various applications, in fact, this one. And you can deploy this any FPGA. And mainly for TinyML application, and we use different kind of weight pruning and dynamic pruning to achieve those power numbers and latency number. And these are the state-of-the-art results which we compared here, but I would skip all these parts. Yeah, so summary is, we have shown these 2 sensory systems, but it's not limited. People are doing olfactory, people are doing touch, people are even non-human like radar. So we are working on the radar side as well in this for different sensory, but more from the neuromorphic principles. And these are the computational system which I talked about, couple of chips like Raman, Aryabhat, and one of the other tab. So those are some of the chipsets which we built. Yeah, and I'll stop here. Thank you.